Tuesday session. So in the early morning session, we will have two talks by Alex and Taylor. Each talk will last for 15 minutes. And after that, we will have a 30-minute discussion session where you can raise questions to both speakers. Okay, Alex, please.
Okay, thanks for the introduction and thanks for having me. The new direction on topological phases I want to talk about with you today is topological phases, namely SPT phases under quantum channels. So this is based on work to appear with Caroline de Groot and Norbert Schuch. So most research that's been done on topological phases is in the context of pure states that are ground states of gapped Hamiltonians. But in the real world, your system in a topological phase is coupled to some environment. And it's natural to ask, what is the effect of this coupling on the SPT phases? So in particular, which SPT phases survive under this coarser equivalence relation where one relates states not just by Hamiltonian evolution on the system, but also by dissipation. So some work has been done on this previously. In this introduction, I want to focus on a particular paper by Coser and Perez Garcia from 2019. So they set out to define a candidate phase equivalence relation that captures physically desirable properties, like the fact that observables should be analytic within a phase, but suffer discontinuities across phase transitions. So what they come up with is to think about states that are related by fast local Lindbladian evolution. So fast here means that the amount of time it takes to drive from one state to another is sublinear in the size of the system. This directly generalizes the more familiar notion of phase equivalence in unitary systems, which is states related by circuits of a depth that grows sublinearly in the size of the system. So an interesting consequence of phase classifications in this dissipative context is that one gets not just a set of phases, but a partial order on phases. And this is coming from the fact that you might be able to drive in a fast way from one state to another, but not go back. So in this talk, I want to discuss a similar idea, but not for topological phases, for symmetry protected trivial phases. So I want to ask which of them survive couplings to the environment, what conditions on channels preserve SPT order. So to motivate this question, let me dig deeper into this Coser and Perez Garcia reference. They give a really interesting example of a fast local Lindbladian evolution that maps any one-dimensional state to a product state. So in particular, any two SPT orders are connected by using this operation. So it seems like there just are no SPT phases, but you might object, wait a second, even in the unitary context, it's the case that all SPT phases are related by circuits. In order to get an interesting classification, you have to impose a local symmetry condition on circuits. So one can try to do this here. This is a channel that's acting on site by site as a tensor product. So the direct analog of the normal symmetry condition is just to say that this operation commutes with the symmetry. And in this case, it actually does. So the naive symmetry condition doesn't save us. According to this equivalence relation, there really are no SPT phases. So what I want to try to do in this talk is introduce a stronger symmetry condition that does in fact preserve SPT order. So to do that, let's dig deeper into the symmetry condition of Coser and Perez Garcia, which I'm going to call the weak symmetry condition. If we write it out in terms of its Krauss representation, we see that we have a channel with two different Krauss representations, and a standard result says that those are unitarily equivalent. Now, if we pick a basis of Krauss operators where that unitary is diagonalized, well, we get this relation, which I've written on the second line. It essentially says that the symmetry commutes with the individual Krauss operator up to some phase. But crucially, that phase can depend on the Krauss operator. It depends on this index I. So this provides just a little intuition about why we shouldn't have expected weakly symmetric channels to preserve SPT order. That's because each of the trajectories that the system is taking comes with a different phase, and there can be interference between these phases. So a first guess at a symmetry condition that preserves SPT order is to say, let's take all of these phases to be the same. And that's what I've written in the third line here and called the strong symmetry condition. When one takes all the phases to be the same, the condition is independent of basis. And before continuing, I should mention that this condition has been written down before in the references here, though it wasn't discussed in the context of SPT order. So to build a little more intuition for what the symmetry condition is doing, let me put it in other terms. So one can work in the Heisenberg picture where instead of acting on states with the channel E, one acts on operators with the dual channel E dagger. So a channel is strongly symmetric if and only if it maps the symmetry operator UG to itself up to some phase, which isn't that interesting physically. Another way to look at strong symmetry is in terms of its purifications. A channel is strongly symmetric if and only if there exists a purification of the irreversible channel to some unitary, such that the unitary commutes with the symmetry, or at least the appropriate symmetry action on the system tensored with ancillas. And finally, to go back to Lindbladian, since that's what we started with, if I have a family of channels that are generated by some Liouvillean, and I write that in Lindblad form, strong symmetry just says that its jump operators commute with the symmetry up to this phase. Okay, so now I want to claim that strongly symmetric channels are precisely the channels that preserve the SPT order of a phase. So to do that, I should review briefly how SPT order is measured in one-dimensional phases. The idea is to take the string operator, which I've drawn here. It is a bunch of UGs, the action of the symmetry on a long string. And at the end of that string are operators O alpha. The end operators O alpha satisfy this condition that I've written in the second equation. O alpha commutes with the symmetry G up to some phase, and that phase is the character of the representation labeled by alpha. So expectation values of these string order parameters are interesting in that they have a pattern of zeros. One can show that the expectation value vanishes unless a special constraint is met. That constraint relates alpha, G, and the 2 cocycle omega, which characterizes the SPT order. So for example, if one is interested in Z2 cross Z2 phases, one can compute this pattern of zeros for the trivial phase and the Haldane phase, and one sees that they're different. So essentially by looking at expectation values of the string operators, one gets a pattern of zeros and can back out the cocycle omega. Okay, so what does this have to do with strongly symmetric channels? Well, I claim that strongly symmetric channels preserve string order. So the bulk of the string operator was just this symmetry UG, and the one way of writing down the strong symmetry condition is to say that the channel maps UG to UG, so that part's fine. The end operators don't get mapped back to themselves, but it's not hard to see that they get mapped to other end operators associated with the same label alpha. So the channel maps a string operator to another string operator of the same class. Therefore, it preserves the pattern of zeros and the SPT phase. So in practice, when one's evaluating string order, there are two components. There's the bulk piece, which I've drawn in red in this picture here. It's just many copies in the thermodynamic limit of some transfer matrix. And in order for this expectation value to not vanish instantly in the thermodynamic limit, the highest eigenvalue of that transfer matrix has to be 1. And one can show that this only happens when the operator inserted in the transfer matrix is a symmetry of the matrix product state. So that's precisely what the strong symmetry condition is stating. So the end operators, on the other hand, don't necessarily get mapped to themselves. They could get mapped to something smaller. So you will see a decay of the string order parameter, but crucially, it'll be a slow decay over time, as shown in this plot here, as opposed to what would happen with only a weakly symmetric or a not at all symmetric channel, where the string order would just instantly drop to 0 because of this eigenvalue being less than 1. And I'll also mention one can show that for a generic state in the phase, strong symmetry is precisely the condition that preserves string order. So it's not unnecessarily strict. So far I've focused just on single site noise because I wanted to deal with this example we had of a channel that destroyed SPT order. But let me briefly mention going beyond that. One can generalize single site noise to channels represented by matrix product operators. The case we've considered so far is essentially the bond dimension 1 case. One gets a similar symmetry condition there, and using some recent results on matrix product unitaries, one can show that strongly symmetric channels again map string order parameters to string order parameters. The only difference is that the end operators get smeared out a little bit because the channel is not acting precisely on site. I also should mention another perspective on measuring SPT order. So instead of dealing with string operators, one can insert a flux on a loop of the system and then act on that twisted sector state with the symmetry. The result is some charge, which is a ratio of a omega GH and omega HG. That ratio determines the entire co-cycle. So in this context, the order parameter is just the action of the symmetry on every site. So it's even simpler to see that a strongly symmetric channel preserves this. And the twisted sector perspective is interesting because there's more potential to generalize it to higher dimensions. These are essentially partition functions of tori with fluxes inserted in the loops. And the strong symmetry condition is saying that those partition functions are invariant under acting by the channel. And I'll just close with a small generalization of the strong symmetry condition. Instead of saying that the Krauss operator commutes with the symmetry, we can say when you pull the symmetry through the Krauss operator, it gets acted on by a homomorphism from the group to itself. This has the effect of permuting the SPT phases. And we've seen an example of this already. The phase that destroyed all of the SPT states from before was actually a strongly symmetric channel twisted by the homomorphism that maps every group element to the identity. So it was mapping every SPT phase to the trivial SPT phase. So with this in mind, we get a picture of what SPT mixed states look like they can be thought of as mixtures of pure states of the same SPT order. The twisted, strongly symmetric channels act within this state, the space of SPT mixed states, but they act in a particular way. Because of the nature of the homomorphism, it can only add to the kernel, not reduce it. These twisted channels can only reduce the complexity or power of a symmetry protected state. So with that, I'll end.
Right. Thank you, Alex. Next speaker is Taylor Hughes.